This is Mrs. Palmer-Quay with the third video for Module 7. In this video, I want to talk briefly about the quantum mechanical model of the atom and end with writing electron configurations using the periodic table. The previous video in this module discussed the model proposed by Niels Bohr to explain why atoms will give off light when they are energized, either by adding electricity or by adding heat or even by adding light. And we call that giving off light emission, and from elements we have atomic emission, and they produce distinct lines of wavelengths of light, not all possible wavelengths, but particular discrete wavelengths that are absorbed and then released as atoms or electrons in the atoms move from a ground state, a low state of energy, to an excited higher state and then return to their normal low state. So Bohr's model worked for hydrogen, and we use it to help us understand what's happening with the other elements. But it begs the question of why do electrons need to exist at these discrete energy levels anyway? The thinking is, if light waves can act as light particles as well as waves, can electron particles also act as electron waves? And there actually is some pretty solid experimental evidence that affirms this that we're not getting into in this course. But incidentally, physicists now believe that any moving object has wave-length motion, but we can't detect it in objects with a large mass because the wavelengths are extremely small. Mass is in the denominator in the equation, and so something with a small mass ends up with a larger wavelength, and it can be detected. So if electrons have wave motion, even though they are a particle, then the orbits of the electrons have to be a specific size to stay in phase. That means that as the wave comes around, again, it matches up exactly. So this example here on the left shows how the wave matches up with itself and fits perfectly, whereas this one on the right, we can see here where it is overlapping and it's not matching up. And so in an electron orbit, this would never happen. This would never happen because the electron would not be able to stay in that orbit, and we know that electrons are stable in their orbits because elements don't fall apart. Because electrons are so small, we can't watch them move. If we shot light at an electron to see it, well, it could absorb some of that light energy and it would become activated and would move into a different spot. So we make predictions about where they may be found, predictions about their exact location or about their velocity, how fast they're moving. But we really are only making probability guesses. This was proposed by a scientist named Heisenberg. So Heisenberg's uncertainty principle tells us that we cannot measure the velocity and the location of an electron. Anytime we try to measure it, we're actually changing something about it. What we understand about electrons, again, based on experimental evidence more so than any actual visualization. We can't see these things. But electron orbitals, where electrons may be found, seem to come in various shapes other than the circles of the orbits like a solar system that Bohr's model is depicted. And so we call these things orbitals instead of orbits because they're not electrons going around as if they were the planet Earth orbiting the sun. There are 4 levels of orbitals. You only need to know 3 of them for most of the course, for most of the elements that we'll be talking about. We have our s orbitals that look basically like a sphere. The p orbitals, there are 3 parts to it, so they all end up being arms on the x, y, and z axis of the p orbital, and they have sort of this called a dumbbell shape, or 2 double spheres on top of each other. Sometimes they're shown a little more elongated. And then the d orbital has 5 different possibilities. This 4-leaf clover that is in the various axes of the coordinate system, and then this funny shaped one on the end, kind of like a donut suspended between 2 dumbbells. In each one of these individual pieces of an orbital, we can have 2 electrons. So an s orbital has a total of 2 electrons. I'll write this in red over here. You have 2 electrons in an s orbital. You have 6 electrons in a p orbital because there are 2 in this grouping and 2 this way and 2 that way. So when your p orbital is completely filled, there are 6 electrons there. And so you can see then in a d orbital we have 10 potential electrons, 2 in each of these 5 different ways that electrons can exist around the nucleus. So at the center of each of these orbitals is our nucleus with the protons and the neutrons, and these various arms of the p orbital will end up, overlaying on each other to occupy all of the axes here of the coordinate system. Electrons are normally found in their lowest possible energy level. That's what we know as the ground state of the electrons. And you remember from earlier videos that the number of protons equals the number of electrons. If you look at this chart, this is listing the orbitals by order of energy level, starting down here. E is going up if you see the arrow, starting down here with energy level 1, energy level 2. You see in energy level 1 we have 1 orbital and 1 s orbital. That would be 2 electrons could be held there. And in energy level 2 we have a 2s orbital. 2 more electrons could be held, a 2p orbital which could hold 6 electrons maximum. If we move up to the third energy level, we have a 3s holding 2 electrons, a 3p holding 6 electrons, and then this funny thing happens, that the s for the fourth level is somehow at a lower energy level than the d orbitals for the third. So when we get to the periodic table, you can see how the periodic table helps you remember this. But for some strange reason, 4s comes before 3d when it concerns how much energy is held in that orbital. So electrons will go into 4s before they will start filling up those 3d orbitals. Even though you would think at energy level 3, anything with 3 must be lower than something with 4. But the s's or the d's slide in after the s's of the next energy level. So to take sodium as an example, to think about how many electrons are in each of these orbitals, you see that the sodium, I have a little block here from the periodic table, and the number for sodium, the atomic number is 11. So we have 11 electrons to go into these orbitals. How will they be found? We start at the very bottom, the lowest energy level, and start filling our way up. So we would have 2 electrons in the 1s level. And we could have 2 more electrons in the 2s level, so we're up to 4. In 2p, we can have a maximum of 6, so if we put 6 electrons in there, then we only have 10 electrons used. There's still 1 more, so there would be 1 in the 3s energy level. And we can write this description as something known as the electron configuration, and really we're just writing out each of these energy levels and putting as an exponent the number of electrons that are in that energy level. So we would write for sodium, it would be 1s2, 2s2, 2p6, 3s1. And that's the electron configuration for sodium. It's really quite easy to write electron configurations if you take a good look at the periodic table. Because over here, if we take our helium and kind of move it to this side, and then we have got this even block, these are the electrons that are in the s orbitals of each energy level. So these are our 1s electrons, and our 2s electrons, and 3s electrons, and 4s electrons. So that's our s block. Over on the far right, we have our p block. And if you look, we've got 1, 2, 3, 4, 5, 6 columns in this p block. Each one of those columns connects to 1 more electron in a p orbital. The transition metals in this middle block here are where we find our electrons that are in d orbitals. And you can see if you look at the numbers, if we come in here on the 4th energy level, here's our 4s electrons, but these electrons will be counted as 3d, because remember from that previous page, the d level orbitals actually come in after the s's of the next highest energy level. So let's use the periodic table to write an electron configuration. And I'm going to pick copper, which is down here in this d block, just to illustrate what you do with the d block orbitals. In order to get to copper, we have to go all the way through energy levels 1, 2, 3, and then part of 4. And so all of the electrons in the periodic table before copper have to be counted in the electron configuration. So let's start on energy level 1, and we're just sort of going our way across the table until we get to copper. What's in energy level 1? Well, there are 2 electrons, 1s2. And then we go through energy level 2. And what's in energy level 2? We've got 2 s2 electrons and 2 p electrons, 6 of them, because all of the orbitals are full. We haven't made it to copper yet. We go down to the 3rd energy level, and we are still not at that block that's copper, so we want to have 3 s2, 3 p6. Now we know that there are some 3D electrons coming because we can see that it's in this 3D block. So leave a little space, because we do want to keep things in order. Even though they're not in order on the periodic table, leave space here for your 3D electrons, and go ahead and write your last 2 for s2. So how many d electrons do we have? Well, we just need to count our way across. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 electrons in the 3D orbital for copper. And that is the electron configuration for copper. 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. Keep your numbers in order, even if you have to leave space to slide those d orbitals in between. This is rather lengthy, and there is a shortcut, and it uses the elements over here on the far right, which are known as our noble gases or our inert gases. You take the noble gas that is just one row up from whatever element you are considering. So in this case, in copper, argon is the noble gas that is one row up. And so we start off by saying it's just like argon, putting the atomic symbol in brackets. It's just like argon, except it also has 3d9 4s2 electrons. So this way you only have to write the electrons that are present between that noble gas and the element that you are writing the electron configuration for. The noble gas shortcut is a whole lot easier to write. So this covers how to set up electron configurations. It's pretty straightforward, working right from the periodic table, and gives you a little bit about the quantum mechanical model of the atom, which is very complex, and we only just hint at it in this class.